Okay, hi everybody. We're continuing our video in coding and cryptography. We're now in the chapter or in the playlist course of mathematics in the modern world. So let's continue. We're now going to deal with the area of cryptography in this module, in the beauty of codes, and let's talk about that. According to Stewart, in his book on page 616, the study of methods to write and solve secret codes is what we call cryptography. Okay, so diplomats and military personnel sometimes engage in highly confidential matters that they need to send information securely by using secret codes. So one may think every time we talk about military personnel, and secret codes, one may think of the Morse codes as one perfect example for that matter. So Morse codes are codes invented by the military, especially by the U.S. allied forces to deliver codes from allies without the opponents knowing the messages. So that's Morse codes, and the process of encoding messages through secret codes is what we call encryption. Okay, so you have a message and you want to convert it into a code that no one understands. Maybe only with the one with the key can understand. So we call that encryption. Okay, so cryptographic programs prevent hackers from using your email address or making calls using your mobile phone to access private information. So actually, the heart of internet security is cryptography. Okay, and the heart of cryptography is or are prime numbers. Okay, so without cryptography, your email or your personal messages might be open to anyone across the internet, but because of cryptography, this allows us to send emails back and forth without no one opening it in between. All right. So cryptography is also used to determine first-hand data communicated through electronic transactions. So according to Stewart from his book, President Bill Clinton and Ireland's Prime Minister Bertie Ahern used a unique signing code and a digital certificate to ensure that an intergovernmental document was really approved by them. So ever since, um, these cryptographic and secret codes have been used throughout history. The first of these is what we call the Caesar cipher. Okay, so the first crypto system was the Caesar cipher, or shall we call it the Caesar code. This is used by Julius Caesar in sending messages to his troops without some spies knowing about it. Okay, so to his most trusted generals. The process was to assign each letter of the English alphabet with integers 0 to 25. A starts with 0, A is converted to 0, and Z is converted to 25. Then, to encrypt a message, replace a letter in the message in position I. Let this I be a certain letter, and you shift it into use three steps going to the right. So that's your cipher. Um, this process actually shifts each letter of the English alphabet three positions to the right. Say we have X, Y, Z are replaced with A, B, C, respectively. So to see the whole Caesar cipher, by default, the Caesar cipher is of shift 3. So we can see the alphabet shifting by 3 spaces here. So for instance, if you want to deliver the message like, say you want to deliver a message, something like a run, using the Caesar cipher of shift 3, how do you make or how you do you encode the word run? So R is U, U is X, and N is Q. So you deliver this to your friend, UXQ, and you know that you need to run, something like that. Okay. If you want to do something like the word secret, say secret. How do you encode that using the Caesar cipher? So S becomes V, E becomes H, C becomes F, R becomes U, E becomes H, and T becomes W. So this will be the message meaning secret for the Caesar cipher of shift 3. Okay, so that's how we use the Caesar cipher. That's how we encode. How we decode is we just do an we just reverse the system in such a way that we can read it going back. So a Caesar shift can be made with different shifting values as to change the encryption algorithm. So see some examples below. Say you have a Caesar shift of 2, so A becomes shifted twice going to the right. So 1, 2, we have the C. C, F becomes H, as you can see. We have Caesar cipher of six, so we have 1, 2, 3, 4, 5, 6. So A becomes G and so on. Caesar shift of 10, so I think you know what the idea. You understand the idea. Okay, so it should be that whenever you're using Caesar shift, your reader should understand the shift, or else he cannot really understand. So one must have the key. We call this the key to the algorithm. Okay, must have the one, or must be with the one you want it, the one you intend to deliver the message to. Now, remember the Geostorm movie? Have you watched the Geostorm movie? Right? So, remember the scene where Gerard Butler is explaining something to his brother in Earth. Gerard Butler is already in a space station, and he's delivering a secret message, and he wants his brother to decrypt or to understand this message here. So, in imagine in a learning task, in the first learning task, you were tasked to decode Gerard Butler's message in the movie Geostorm. It was mentioned that his phone number is 19929555871. That's the clue. The sentence says, "You remember that the day took us fishing? Yeah, he dropped his cell phone in Key Biscayne. This gave us the clue for the phone number, where every number determines which word is to be used for the hidden message." So the following underlined words are the words of the hidden message. This is the whole script of Gerard Butler in that movie, and the hidden message is within it. So the key is the number, because we have the first statement to be. You remember the day that dad took us fishing? Yeah, he dropped his cell phone in Key Biscayne. So cell phone in Key Biscayne. So that's the idea that tells his brother that the the key or the algorithm is from the cell phone number. So if we're going to move, one becomes proof, and then we're going to move 9 steps from there. So we have 9 words rather. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the next word, and then 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then another 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 2, 1, 2, and then after 2 we have 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. After that we have 5, 1, 2, 3, 4, 5. We have another 5, 1, 2, 3, 4, 5, and then after that we have 8, 1, 2, 3, 4, 5, 6, 7. This is one word, 8, and then we have 7, 1, 2, 3, 4, 5, 6, 7. We have 1, and then that's the end of it. So if we're going to read it, so we have proof of sabotage at highest level of government. Trust no one. So that's the key. That's the message of Jared Butler's brother on Earth. Okay, so that's from the movie Geostorm. You may watch it if you have the time. Okay, now the coding scheme that was used there is simple, yet it's brilliant. So the process by which we were able to take off the important words is what we call decryption. Okay, we call that decryption. So let's have some vocabulary here. We call plain text the unprocessed or raw message that needs to be transmitted securely. Okay, so it's unprocessed, it's raw message. It's a raw message. We call it a ciphertext when the result of encryption is performed on a plain text. So you have a plain text, which is can be read by us. You encrypt it, and after that encryption, the process encryption, it will become a ciphertext. Okay, so encryption is the process of transforming information, the plain text, using an algorithm, a cipher, or a key to secure it and making it unreadable to anyone else. After encryption, it will become a ciphertext. Oppositely, if you want the ciphertext to become a plain text, what we call that decryption. Okay, it is a process of decoding a ciphertext to reveal its plain text. So, if we're going to clear this up, plain text going to ciphertext is what we call encryption. Okay, ciphertext going to plain text is what we call decryption. Okay, so hopefully you understand that. Okay, so let's move on. Let's give some exercise. I'm going to give you this statement, and using the Caesar cipher, what is the answer? So I can give you, you may pause the video for this. You may thought of what Caesar cipher, what shift. By default, the Caesar cipher will be of shift 3. Okay, so you may pause the video again. So what's the answer? Okay, so the answer is pretty much mathematics in the modern world. Okay, for those who got it, so congratulations for you guys. Okay, so next is the Caesar's cipher is just an it's just easy to decrypt, especially in the modern era. There is, however, another algorithm that presents a better security than that of the Caesar cipher, and that algorithm is what we call the decimation cipher. Okay, so let's finish this with this part. Decimation cipher encrypts a message by multiplying each value. Remember, in the Caesar cipher, what we do is we just add the shifts. We add some numbers to the shifts in order the shift will be moved entirely. Okay, this decimation cipher multiplies each value, okay, by a fixed number. Each letter in the message is replaced by A to 0, B to 1, C to 2, up until Z to 25. Maybe you're thinking why it only ends with 25, because we started A with 0, not with 1. Instead of adding like the Caesar cipher, like I have mentioned, the decimation cipher multiplies the position values by an encryption value. So multiplication is done by modulo 26. Okay, modulo 26. Replacing the resulting products with their corresponding letters generates the encrypted message. All right, so modulo 26, I think if you want, I can give you the video. Maybe you can see that above, the video about modular arithmetic. Okay, so to give you an example, imagine a clock. So our regular clock, what you can see now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, is of modulo 12. Every time we go beyond 12, what we do is we divide the number by 12 and then get the remainder. The remainder will be the answer then. So what is, when you say, what is 13? 13 hours, 1300 hours. So in military time, two of modulo 12 in the regular 12-hour period format. So what we're gonna do, how do we get the 13 mod 12? It's just equal to what number? 13 divided by 12 is remainder 1. Okay, remainder 1. So therefore, that's your answer. It's 1 o'clock. When you say 13, it's 1 o'clock, or 1 p.m. to be exact. So that's what we do similarly with modulo 26. We just imagine a clock with 26 hours. So every time we go beyond the 26, we just divide it by 26 and then get the remainder. And the remainder actually is our answer. So for instance, when you have the number like 28 modulo 26, you just get the remainder and it's equal to 2. Say you have 30 modulo 26. You divide the 30 by 26, we have 1, remainder 4. Okay, we may also try 55 mod 26. So 55 divided by 26 is 2, because 26 twice 26 is 52. So the answer here, the remainder is 3. So that's your answer. Okay, so replacing the resulting products with their corresponding letters generates the encrypted message. So the Decimation cipher is a simple substitution cipher after assigning the numbers 0 to 25 in the letters in the English alphabet in order, and then select an odd integer. It should be an odd integer p, and then the p should be between 3 to 25 except 13, because 13 is a factor of 26, and it cannot be. So what are the steps in the Decimation cipher? So steps: assign the 26 letters of the English alphabet from 0 to 25. So that's automatic. So these are the numbers here. So assign A as 0, B as 1, C as 2, and then so on up until Z is 25. Then you select an odd integer. We call that P between 3 to 25 except 13. So you can either choose 3 between inclusively 3, 5, 7, 9, 11, 13 is not, 15, 17, 19, 21, 23, 25. There. So you just choose either of those numbers to be your P, and then you replace a letter in the message with position I with the letter of the numerical value P times I. P times I modulo 26. And the P is what we call the key. So let me give you one instance. So for example, we're going to encrypt the message biology is a natural science. And we're going to make use of a decimation cipher of P equals 5. Okay, so let's do the steps here. So we're going to show the steps. What we're going to do is we're going to first have the message. So we have biology is a natural science. We convert these words into numbers by using the table that we showed before, this one here. So we convert all the letters. B becomes 1, I becomes 8, O becomes 14, and so on. So we can see that there. And then since our decimation cipher is equal to 5, hence we will be multiplying all of them by 5. Okay? After multiplying all of them by 5, what we need to do is to get the modulo 26. In order for us to get the number, we need to put them back in letters, right? So we need to have these numbers, which is all modulo 26. So we're going to multiply that by 5 and then divide all of them by 26. If it's not divisible by 26, so therefore we just write it, copy it right off. So for example, here, 40 divided by 26 is 1. The remainder is 14. So the answer is 14 here. 70 is 70 divided by 26 is 2, remainder 18. So that's the answer. So we just follow that in all of the numbers, divide it by 26 and get the remainder. And then afterwards, this message here, we can all now convert it, making use of this table here, we can convert it into ciphertext. So this is our plain text. This is now our ciphertext. Okay, and you give this message to your classmate or someone, and you tell them that this is decimation cipher P equals 5, and they need to understand that. Okay, and that's a process of decryption now. Okay, this is how anyway you encrypt the decimation cipher. To decrypt it, you need another process for doing so. Okay, so next is let's talk about the decryption values. Okay, again, the opposite of encryption is decryption. So when we decrypt, of course we will do the opposite the way, but notice if we're going to divide them by 5, it's not so good, because if for instance 14 divided by 5 is it has a decimal. 18 divided by 5 has a decimal, so you need to find another way to do that. So we need to have the decryption values for the decimation cipher. So for instance, if you chose an encryption value of 3, your decryption value will be 9. If your encryption value is 5, your decryption value will be 21. If your encryption value is 7, your decryption value will be 15, and so on. So this depends on the problem that we have. So example, if we have an encryption value of 5, you will get the decryption value of 21. And then the next line, say for instance you're the classmate there, and you need to understand this. So for us, say we understand this already, and if you're the classmate that you have this kind of message, you need to decrypt this. So how do we decrypt in decimation cipher? So we decode the message using the decimation cipher P equals 5. So if P is equal to 5, what is the decryption value? Going back in this table, the decryption value is 21. So we'll let our decryption value, which is denoted by your J, to be 21. Okay, so that's 21. So how do we do this? Let's do this in process. Let me type this J equals 21. Okay, so first we will write the message. So write the message as it is, the ciphertext. We want to convert it into plain text via decryption. We put the numbers in, so we convert all the letters into numbers. The same table will be using the same table. I mean this table here. Okay, and convert them into numbers. And from that, we will use now the decryption value, which is 21. What we're going to do is we multiply each number by 21. Okay, multiply each number by 21, what we will have is this. Okay, is this. Therefore, what we all have are these numbers. These are just numbers multiplied by 21. Next, we're going to apply mod 26. That is, we're going to divide all the numbers by 26, get the remainder, and that will be our new found answer. Okay, so for instance, 105 divided by 26, okay, is some number with remainder 1. Okay, so 104 with remainder 1, and so on. You continue that process. Okay, and then finally, with these numbers now, which are in mod 26, you can now clearly convert them into letters, making use of this same table over here. And what we will have is biology is a natural science. So this is how we do the encryption and decryption in Decimation Cipher. Okay, so that's it for this video. Thank you very much for watching, everyone. I hope you have understood something here, and I'll see if I can create one more video to illustrate the Decimation Cipher more and more. So thank you very much again. See you and God bless. Keep safe. Thank you.